welcome to the lecture of this finite volume method. Now, if you move forward and try to find out the point, let us say I have this kind of systems which are not so called looking like an uniform system. I have a point here, I have a point here, I have a point here, here and here. These are the function which actually represent these points, and the distance between this is dx, and I try to find out a position which is the exact location from this point to this h distance, and I try to find out the derivative at this location. So, how do I calculate? Because this is this particular point, that yellow mark point, it does not belong to neither of these nodal points. So, it is somewhere in between this point and this point. So, I have to get some sort of a weighting function or weights which can actually represent properly to find out the derivative at that point. Okay. Now, how do we do that? So, try the Taylor series expansion. Okay. So, we try to find out f x. Now, I have a point here and I have a point which I am interested here. So, this is a distance dx. So, I write x plus dx approximated as f x plus f prime x and dx. Okay. So, this is the point of my interest, and then I write. So, this essentially writes the forward formula. Okay. And the second one, you go back to the, so this is the point where f x is defined. So, this is actually the backward formula. Okay. And this is approximated as f x minus f prime x dx. So, you get back these two system. Now, what are we looking for? We are looking for something like, we want to, this I stands for the derivative, order of derivative. That means, if I is 1, that means I am trying f prime. If I is 2, I am trying f double prime. If I is 3, I am trying for f triple prime. So, it actually tells you the particular derivative that you are interested in with some sort of a weight function, and then this index function where the f x is defined. So, you want to write something like that, but in a more generic form. Once you can come across with this, then you can devise any derivative with any sort of points. So, essentially this is very useful to find out a generic expression for any order of derivative. So, whether I want first order derivative, second order derivative, and what is the order of accuracy I want, everything can be kind of calculated for. Now, you put some sort of an algebraic system. So, I want to derive a second order system. Okay. So, my numerical system should be second order accurate. When we talk second order scheme, so these are all sort of a synonyms. When we say that the second order scheme, these are second order accurate system. So, when you say that second order accurate system, so you get, so if you go back here and look at this expression in equation 1 and 2 and write down a f plus equals to a f plus a f prime dx. So, which is this expression f x plus dx. So, x plus dx is nothing but represented as f plus or f I plus 1. Similarly, f x minus dx is f minus, which is equivalent to f I minus 1. Okay. So, first case, this is equation 1 multiplied with a weighting factor A. So, A is unknown here. So, A, B, these are unknown, and what we are trying here, we are trying to find out A and B in a systematic way, so that you can get an expression which is second order accurate. Okay. In order to find that, you multiply the system with A, first system, so you get an expression like this. You multiply the second system with B, you get a system like this. So, if you compare, my x plus dx is approximated like this, x minus dx is approximated like this. So, this guy is multiplied with A, this guy is multiplied with B. Once you multiply it, you write A plus approximated at A plus A prime dx, number 1, number 2 B minus approximated as B prime dx. So, you get back 2 more system. So, essentially equation 1 and 2 multiplied with A and B get back to this system. Once you get back this, you add up. So, you add them together. If you add them, left hand side you get this expression A plus plus B minus, which is equivalent or approximated as A plus B and A minus B A prime dx. So, this is what you get at the right hand side, okay, and this is what you get at the left hand side. Now, if you see, you have two unknowns and you got only one equation. Now, you have to solve A and B to find out the solution. So, how do you find out the solution? Because once I find out A and B, that will lead to the particular derivative. So, how do you find out the solution? Because now from this particular expression, I can actually devise the system of equations where, so essentially what I need, I have two unknowns, so I need two equations, then only I can solve for A and B. Okay. So, from this particular expression you can devise that. One set, you say that I only want the interpolation, I do not want any derivative to be present. That means these functions A plus and F minus, if I want to only calculate the interpolation, then I need to get interpolation between A plus and F minus. So, that will have some values of A and B. Now, some values of A and B only get me interpolations. So, that will retain. So, if you look at, here is my function f x, here is my function x plus dx, and here is my function x minus dx. So, this is my f plus, this is my f minus. So, what I want that the function to be interpolated at this point, and I have an expression like this, or I have an expression in hand, then f plus f minus can be retained, f can be retained. We do not need to have this derivative term to be present. So, when I am only interested in interpolation, I do not need this term. So, theoretically f prime cannot be 0 because this is having a finite value, dx does have some finite value. So, the term which can be taken to 0 is a minus b. So, that leads to the one equation. Secondly, I am trying to get an interpolation. So, this should be 1. That means, in the interpolation of these functions, I will retain the left hand side, which would be also retaining this portion, no derivative. So, that leads to two equations. So, if I solve these two equations, I will get a value for A. See, one can quickly find out the value for A would be half, and b would be also half. So, if I put half and half and half and half, so I get an interpolation value, I do not have any derivative exists. Now, if I want the derivative to be present, that means I want, let us say, f prime. So, the derivative to be present here, what I need, I do not need this interpolated values. So, a plus b goes to 0 and a minus b, that becomes 1 by dx. Why? Because I want only f prime to be present. F prime to be present here, I have to get rid of completely this term along with this dx. So, no matter what value a minus b has, it should be divided by dx. So, this dx gets cancelled off, you get a system of equation. Now, from here if you solve, you get the weights. Now, if you write in a matrix form for the interpolation where only I am interested, so equation that I had in the interpolation, a plus b equals to 1 and a minus b equals to 0. So, I write 1 1, 1 minus 1, a b 1 0. So, this is the matrix. If you solve, you get the system. So, theoretically a should be half and b should be half. One can solve either this matrix or one can solve, and the other case a plus b equals to 0, a minus b is 1 by dx. So, if you put them together in the matrix 1 1 0 1 minus 1 1 by dx. If you solve that, so here if you look at this a, b, these are nothing but the weights that is used to find out the derivative. Now, if you calculate that and the result, as I said, for interpolation a and b would be half and half, and in this case a and b would be, so here a is 1 by 2 dx, b is minus 1 by 2 dx. So, essentially if you look at these two, the derivative and the interpolation, there is a nice similarity. One case you get half half, other case the half half is sitting there, but 1 by dx is also sitting there. So, now the question is that can we generalize this idea, this weighting idea, and use it for the other operators, or maybe trying to find out the higher order derivative. So, certainly we can. How do we do that? Again, the underlying story or the theory which remains same is the Taylor series expression, but we have to now expand the Taylor series expansion for other term and then finding that. How one can do that? Let us look at it one after another. So, again we will concentrate on a system like this, simple system where f(x) is defined, you have x plus dx, you have x minus dx, and these distance are given as dx. You can also have one point ahead of it, x plus 2 dx. Okay. So, first thing that we want to find out x minus 2 dx, that means the point which is, this is my point of interest, the point which is staying here, x minus 2 dx, and this distance between each point, they are uniform and dx. So, x minus 2 dx, again I am approximating using the function at f(x). Okay. So, f(x) which is written as f(x) minus 2 dx f prime plus 2 dx square factorial to f double prime minus 2 dx cube factorial 3 f triple prime and so on. Okay. This particular equation you multiplied with a. Okay, that is my first equation. So, here what we are trying to write here is that we are trying to generalize this idea for higher derivative, and to do that let us consider these 5 points. One is x, x plus dx, x plus 2 dx, x minus dx, x minus 2 dx. Okay. Now first find out f minus 2 dx, then we find out x minus dx. That means using the value at x, I try to find out the function value at x minus dx. Again f minus dx f prime dx square factorial 2 f double prime minus dx whole cube factorial 3 f triple prime and so on. Now these are the points. Now this guy is multiplied with b. Now you look at the point which is ahead of it, that means x plus dx. So the x plus dx would be f plus dx f prime dx square by factorial 2 f double prime dx cube by factorial 3 f triple prime and so on. And the last one, this guy is multiplied with c, and the last term which you want to evaluate at x plus 2x. So x plus 2x is f plus 2 dx f prime 2 dx square factorial 2 f double prime 2 dx whole cube factorial 3 f triple prime and so on, and this one is multiplied with d. So essentially I want to find out the derivative, and I have adapted points, 2 points behind that particular point and 2 points ahead of that, and all of them are differed by a distance dx from the preceding one. So essentially the distance between the points are uniform and they are given as dx. And now each of these equation, first one multiplied with a, second one b, third one c, last one d. And what we are trying to find out? We try to find out any derivative. It could be first derivative, it could be second derivative, and you can also find out third derivative. So you can find out, but let us see what happens to first derivative or the second derivative. And as we have done earlier, you add up these things together. Okay. So all these equations multiplied with a, second one b, third one c and d, after multiplication you add them together. Okay. So what it gives you back? It is a very nice expression. So here x minus 2 dx, which is equivalent to a minus minus, that is what you see here, a multiplied with a minus minus, x minus dx equivalent to a minus, second equation multiplied with b f minus, x plus dx equivalent to a plus, and f x plus dx 2 dx equivalent to a plus plus. So that is here. So if you just have this, essentially f minus minus, this is f minus, this is a plus, this is a plus plus, f minus minus multiplied with a first term, and second term equation multiplied with b, that is the this equation, third equation multiplied with c, that is c a plus, fourth equation is multiplied with d, that is f double plus. Now once you collect the term together, now you see if you multiplied with a, you get af here, and we are adding them together. After multiplication you are adding them together. So you get here af, a into 2 dx f prime, a into like that. So af, bf, cf, df. So you collect them together. So this is my left hand side, and this is completely my right hand side. And right hand side, what you get? If you collect them together, this is what you get, a, b, c, d. Now you collect all the term corresponding to f prime. So f prime, first equation is multiplied with a, so minus 2 dx, second is b minus dx, third is c plus dx, last one d 2 dx. So you collect dx f prime outside, minus 2x minus b plus c plus 2d. Now similarly, you look at the third term, second derivative. So that is having 2 dx square by factorial 2, all of them, this one multiplied with a, this one b, c, d. You collect them together, dx square f double prime 2a. The reason is that you get 4 here divided by 2. So 2a plus b by 2, here you get dx square which is outside 1 by factorial 2. So b by 2, third case also c by 2, fourth case 4 by 2, 2. So you get 2a, b by 2, c by 2, 2d. Now remains the third derivative. Here 2 cube is 8 divided by factorial 3. So there will be factor dx cube, here dx cube multiplied with b, here dx cube multiplied with c, here 2 dx cube d. You collect dx cube f triple prime minus 8 by 6a, that comes from this particular term with minus sign. Second term b by 6, that comes from this term. Third term is c by 6, comes from this term. Last term is 8 by 6d. Now you get a system with all a, b, c, d. Now if you look at this particular system, you have a left hand side, right hand side and your number of unknowns. Number of unknowns here 4, a, b, c, d, but equation you have, so number of equation is 1, just like previous case. Previous case we had 2 unknowns, 1 equation, but we have devised 2 different system and solved for a and b. Similarly here we have 4 unknowns, so at least to get solution we need 4 equations. So how do we derive those 4 equations? As we have done earlier, we can find out these coefficients by mapping the coefficients from one side to another. Now as we have done, first we are interested in the interpolated value. That means all these points fx, x plus dx, x plus 2 dx, x minus dx, x minus 2 dx. I want everything to be interpolated. If that is the case, left hand side will be there and right hand side, this guy a plus b plus c plus d should be 1, because I want only interpolated value. Any other derivatives which belongs to this right hand side, they must be 0. That means a plus b plus c plus d should be 1, minus 2a which is connected with the first derivative minus 2a minus b plus c plus 2d, they must be 0, that is second. Second derivative is connected with 2a plus b by 2 c by 2 plus 2d, that is 0. Third derivative connected with minus 8 by 6, 1 by 6, 1 by 6, 8 by 6. So that is also 0. So you get a system of equations. Now here if you look at it, you got a, b, c, d, you got 4 equations. Now one can solve algebraically, one can convert them to a matrix and find out the solution. So again for interpolations, if you put them together, a, b, c, d 1, so the first equation corresponds to the first system. This if you put the coefficients a, b, c, d 0, 0, 0, you solve this matrix, you get a equals to minus 1 by 6, b equals to 2 by 3, c equals to 2 by 3 and d equals to minus 1 by 6. So all these weights if you use here A, B, C, D that you have got, if you use, all these derivative terms will vanish, they will disappear, only thing you get some interpolated value. Now similarly we can get first derivative. If you want to find out the first derivative, that means you are looking for f prime. So if you look at that, here a plus b plus c plus d, so this and a prime is connected with this, so this will be there. Any term which is connected with f double prime, they would be 0. That means this term would be 0, this term would be 0, and only first derivative term would be there, and this guy would be 0. So the first derivative a plus b plus c, which is connected with the f, that function, that is 0. Term which is connected with the f prime, that is giving 1 by dx. Term which is connected with the f double prime, that is also 0. Term which is connected with f triple prime, that is also 0. So you got a matrix. Once you solve it, you get A equals to 1 by 6 into 1 by 2 dx, essentially 1 by 12 dx. B equals to minus 4 by 3 into 1 by 2 dx, that means 2 by 3 minus 2 by 3 dx. C equals to 4 by 3 into 2 dx, again 2 by 3 1 by dx. D equals to minus 1 by 6, so 1 by 12 dx. Now if you see, interestingly, the points are like this. This is my f, this is f plus, f double plus, f minus, f double minus, which is equivalent to fi, fi plus 1, fi plus 2, fi minus 1, fi minus 2. And if you look at it, that the weights which are multiplied, they are uniformly distributed. One is A and D, they are connected with this point and this point of the system, because if you relook back the equation, A is multiplied with f double minus, D multiplied with f double plus. So A is multiplied with this, so the weight is 1 by 12 dx and D is 1 by minus 12 dx. B and C, which is multiplied with, this is B, this is A, this is D, this is C. So if you see, the weights A and B are having equal values with different sign. B and C, they do have same value but with different sign, and you are trying to find out. So you are trying to find out the derivative of fi, and taking 2 points ahead of it and 2 points behind that, essentially they becomes, this is centered derivative. That is why you have equal weights of A and D, but opposite in sign. You have equal weights of B and C, that is also opposite in sign, and then you evaluate the f prime at that location. So this is essentially centered derivative involving 5 different points. When you involve so many points, this actually leads to the stencil, or this is called the numerical stencil that you have to find out the derivative, and we will look at it in the next lecture. Thank you.